Here we're looking at a fairly typical AP free response problem. It's essentially going to be what I'm going to refer to as like integrating a rate function for the majority of the work. We've been given a story about Kathleen skating on a straight track, and we have information about her velocity at which she's skating at these different times along the way. It's defined for 0 to 12 seconds. And we've got our units of feet per second as far as the velocity goes. Time is going to be in seconds. And the first question says, uses the data in the table to estimate her acceleration at time t equals 4. Really, really typical first question when we've been given one of these table problems. So acceleration, of course, is the rate of change of velocity. And since we're being asked to estimate it at time equals 4, we're just going to look to see where time equals 4 exists in our little picture here, and that's between 3 and 5. So I'm going to refer to this, as I have many times, as essentially a 7th grade slope problem, where all we have to do is compute the average rate of change of the velocity, which is going to be the average acceleration between 3 and 5, and that's going to estimate her acceleration at time equals 4. So we're going to do essentially, well, I should really use k, because that's what they're calling the time here. So we're going to use k of 5 minus k of 3 over 5 minus 3. So that's the velocity at 5, which is 10, minus the velocity at 3, which is 5, over 5 minus 3, which is 5 over 2. And it says include the units of measure. This is always really easy because the numerator has units of measure of feet per second, and the denominator is units of time, which is seconds, so feet per second, or 5/2 feet per second squared. And that is a real easy way to pick up probably 2 points on the rubric for this, maybe one for the numeric value and one for the units. It might only be 1 point, but chances are it's 2. And in almost every single one of these problems where we're given a table like this, we'll be asked to do some sort of a Riemann sum, which is going to be used to approximate an integration. We don't know what function created these data points up here. We don't have the specific k of t. But I always like to just take a couple, it takes less than a minute, draw a quick little coordinate plane and kind of get a sense of what's happening in this thing. Now, up at in the original statement of the problem, they say that her velocity is differentiable and it's increasing. Well, it's important to know it's differentiable so that we could compute like an acceleration, an instantaneous acceleration, meaning that we can take the derivative of velocity anywhere from 0 to 12. And secondly, they say the velocity is increasing. And of course, it looks like it's increasing here, but for all we know, if it hadn't said that at time equals 2, for example, who knows, maybe the velocity would have been up here, and we would have had a graph that would have come up and come back down, and maybe gone up and come back down countless times in between these particular data points that we have. So them telling us that it's increasing is helpful information to get a basic idea of what's going on, but I guarantee it's going to come up a little later in the problem, and it's going to come up here when they talk about whether it's an overestimate or an underestimate for this integration that they're asking us to do. So they say use a right Riemann sum with 4 subintervals indicated by the data in the table to approximate the integral of 0 to 12 for k of t dt. So essentially what they're asking us to do is to approximate, I'm going to go ahead and kind of just connect this with a curve, if you will, just so we could kind of see what k of t might look like. They're asking us to approximate what the integral of k of t would be like, which of course is the area underneath that curve between 0 and 12. And so they said use a right Riemann sum. So what that means is we're going to go to the right side of each interval, and they say use the 4 subintervals indicated by the data. That basically means they've already kind of done the work for us. There are 1, 2, 3, 4 subintervals that we get naturally just using this data. And because it's a right Riemann sum, they just mean use the height of the rectangle that we're going to use determined at the right side. So we're going to approximate that area under the curve by using the areas of these 4 rectangles added together. So all we have to do is find the area of this, each one of these rectangles. I'm going to put little Roman numerals in there just so we can follow along. And the area of the first one is 3 wide by 5 tall, because we're using the height over there on the right side, so 3 times 5 for area 1. And we're going to add that to area 2. which has a width of 2, from 3 to 5 is 2, and a height of 10. So 2 times 10. Then we're going to add the area for part 3, which is 3 wide and 20 tall. So 3 times 20. And we're going to add that to the area of the 4th region, which is 4 wide and 24 tall. And we're just going to add these numbers up. So we've got 8, and then 20, and 60, and 24 times 4 looks like it's 96. So now we're going to add these guys up. Let's see, 20 and 60 is 80, plus that extra 8 is 88, and 96. So here we go. 184 seems about right. And so we've now integrated that thing, and we have a numeric value for the approximation of the area that would have been under this curve that I'm kind of showing with the red shading as 184 square units. Now they said indicate units of measure here. Well, we have to think about what's going on here. The vertical axis is feet per second, and the horizontal axis is seconds. So if we were to multiply feet per second by seconds, which is what we're doing when we're getting an area, of course we're going to get feet. So the answer to that integral, which we could write as 0 to 12 k of t dt, is approximated to be 184 feet. And as far as our calculus goes, we should understand that it is going to represent kind of the net change in distance that's occurred during those 12 seconds. They didn't ask us that to interpret it, but that's what it would represent from where the person was at the initial time, for the initial position at time equals 0, and at the end of the story, after 12 seconds, the person had changed its position by 184 feet. It does say, is this approximation an overestimate or an underestimate? Well, it's really clear from my drawing that the blue region is considerably larger than the red region. Now, to explain your reason, we could say this is an overestimate, and again, the fact that they told us that the velocity function was increasing, you can sort of see that as if we know the function's increasing as it moves up through these points, if we're using a right endpoints, we're going to capture area that's not necessarily under the curve. So all we really have to say is an overestimate as velocity is increasing on the time from t happening between 0 and 12 seconds. I think that would suffice to offer justification there. For part C here, we're now introduced to Nathan, who's skating on the same track. He starts out 5 feet ahead of Kathleen, which is probably going to be important in the context of this problem, at time t equals 0. And he's got his own velocity function, which we actually have, an algebraic expression for. And it says, write but do not evaluate an expression involving an integral that gives Nathan's distance from the starting line at t equals 12. So, if you remember Kathleen's story, at time 0, I think we knew that essentially her position was 0 at the starting line. And now we've got Nathan starting here at 5 feet ahead at time equals 0. So whatever distance he travels, net distance he travels during these 12 seconds, we're going to have to include the fact that because they're asking about his distance from the starting line, we're going to have to include the fact that he started 5 feet off the starting line. So his position, or his distance, maybe we could call it d of t, for Nathan's distance at the starting line, is basically going to be the integral of the velocity function. It's going to tell you net distance changed over that time. And notice they say write an expression involving an integral. But we don't want to lose the fact that he starts at 5 feet. So he's starting at 5 feet, and then we're going to add whatever change in position that occurs over that time, which would be the integral from 0 to 12, because there's 12 seconds involved, of his velocity function, which is, the 150 over t plus 3 minus 50 50 e to the negative t, put parentheses around all that, put a dt there, and that's all we need. Because this portion, the integral portion, is going to tell us his net change in position during those 12 seconds, and the 5 are going to, represent where he started. So he starts out 5 feet to the right, and then this is going to represent whatever however that position changed during those 12 seconds. All right, I might consider this fourth part, part D, maybe a little bit of a throwaway question on their behalf. They've given us a velocity for Nathan, a velocity function up here, and they're asking for an acceleration function. And if there's one thing we're certainly going to know going into the exam is that acceleration is simply the derivative of velocity. So essentially, they're just taking one portion of this one free response question, asking us to determine the derivative. So if we wanted to call Nathan's acceleration a of t or something like that, we just need to take the derivative of this velocity function. So for this first portion that we have here, that's a quotient. We could do the quotient rule on that. Or you might, some people hate using the quotient rule, so they might call that part 150 t plus 3 to the negative first, and just treat it like a little bit of a chain rule thing, bringing the negative 1 down in front, dropping the power by 1, and then taking the derivative of what's inside. So what the heck, I'll do it that way. So bringing the negative 1 down in front, we're going to get negative 150 t plus 3 to the negative second, and then we're going to take the derivative of what's inside, and the derivative of what's inside, t plus 3 with respect to t, is just simply 1, so there's really not much going on there. Now we're going to add to that the derivative of negative 50 e to the negative t, which of course, if you have a exponential expression with e as the base, it's the derivative of e to the whatever is e to the whatever multiplied by the derivative of the exponent, which is in this case negative 1. So cleaning that up, we really just have negative 150, which would be over t plus 3 quantity squared. That's what the negative 2 exponent would do. This negative and this negative would come together to be a positive, and we'd have 50 e to the negative t. And there's an acceleration formula for Nathan. And it looks like that's all we have for that problem.